I'd like to welcome everybody here in the room, and we have 90 people in the room here at least. So you're all very welcome to this Engineers ICME talk, and I'd also like to welcome all the members of Engineers Ireland and the ICME who are listening in online. My name is Cillian O'Sullivan, and we're live here from Munster Technological University in Cork. You can see the fire exit, folks, at the bottom left and top left of the room. What will happen for this talk is I'm making a few remarks just to get us launched. Kevin and Maria will give the lecture. After the lecture, we will have questions from people in the room and online. So if you have questions online, just put them in the chat function, and Sean Devlin will give us those. Just before we start, we have a couple of forthcoming events. Next Wednesday at 12:30, the later time, we will have Owen Field and John Scott of BSI Technologies giving their pump school. Engineers Ireland Chem Division will also be visiting Medtronic Medical Device Factory in Galway on Friday the 27th of February. And the Institution of Chemical Engineers All Ireland member group will have their annual dinner in the Maryborough House Hotel on Thursday the 5th of March. Just before we start, I'd like to thank Kate Markey of Engineers Ireland, Jay Cotter, John Devlin and Alina Daly for their help in setting up the event, and to Brian Coffey give the vote. Thanks. We have two speakers today. Our first speaker will be both from PM Group. Dr. Maria Sierra Martinez has worked with PM Group for the last 4 years. She's an expert in the area of pressure relief devices. She obtained her PhD in chemical engineering from the Universidad Complutense de Madrid. Kevin Gibson is an Associate Director and Process Engineer at PM Group. He's just finishing his PhD within the next week or two. He was a member of the working group developing industry-wide standards for buffer skids in the BioPharma industry. They're both coming from PM Group, which is based here in Cork, has over 3,000 staff, and they're designers and creators of high-tech facilities with advanced technologies and novel features. We see them in the pharma industry, but they're doing a lot in data centers and all kinds of facilities engineering. So without further ado, I'll hand you over to Maria to start the talk. Thank you.
Hi, everyone. We are going to give a few review of what's buffer management. So this is going to be the agenda. I'm going to start with an overview of buffers, what design considerations we will have to design this, what methods of buffer preparations there are, and then Kevin will continue talking about the buffer stock blending preparation systems, like what was the design and performance. He's going to talk a bit about economics and environmental, continuing with a bit of industry trends, and he will finish with what we think is the future for buffer management. If I start with overview of buffers, so buffers are critical components of the biopharmaceutical industry because they have a great impact on the process robustness, in the process quality, in the yield, and especially in cost. For the production of 1 kilogram of a typical monoclonal antibody, around 1,500 liters of buffers are required. And this is not just of a single buffer, but rather like 15 to 40 different buffers. So a buffer is an aqueous solution of a weak acid and base pair, and a salt is normally added to set the ionic strength of the solution. The most important property of the buffers is like they keep the pH invariable when small quantities of a strong acid and salt are added. So they are normally used upstream of the process to optimize the conditions for cell growth and expansion, or downstream to assist with the protein purification, control the ionic strength that is very important for the chromatography operation, and to stabilize the protein and ensure that it has the optimal biological activity for its commercialization. Across the industry, we have like 10 raw materials that make up for more than 90% of the buffers that are used for bioprocess. This is very important because, like, many of the buffers share the main share the same components, and this means like we can standardize a bit the production process. However, the buffer preparation design, it's one of the most complex aspects of a facility design because they present many challenges. Some of the challenges are like they have a high capital cost involved because you require new equipment to be installed or you have to replace the equipment. The operating costs are very high too because of the large volumes that are required to produce the final product. They have like a huge impact in the footprint of the plant. They have ergonomic challenges, and they are normally a bottleneck for the process because you require like large volumes in very short period of time. They are dependent on the product mass. So this means like if we increase the production on the bioreactor, we are going to have more protein delivered to downstream process. And just to cope with that, we have to increase the capacity of the resin used in chromatography, or you have to increase the number of cycles. That is going to increase the number of buffers that are going to be used. This is coupled with an increase of the Wi-Fi consumption. So we will have to produce more Wi-Fi to be able to prepare more buffers. That Wi-Fi has to be also stored. The extra capacity of the buffers will require extra capacity to be prepared, and they will have to be stored. And then we are going to have more waste. So even though this looks very complicated, it is feasible. It can be feasible sometimes, but it's going to have a great impact in cost. But it's true, like for certain existing facilities, when you increase the number of buffers significantly, you can have a bottleneck. And this bottleneck is just a schedule problem that is dependent on the buffer availability and how the equipment is operated. So what you can see now in the screen is a diagram from Schedule Pro that represents different buffers and how they move across the production steps. So each color is a buffer, and you can see like the buffers are delivered to the downstream processes with an interval of very few days. Like this can be 2 to 3 days for a very throughput process. And what this translates in, like, you need to have the buffers prepared and ready to use in that short period of time. Furthermore, like each preparation equipment it can only prepare one buffer per shift. Like a buffer typically takes between 8 to 12 hours to be prepared. And this is independently of the demand or the conditions that you have. So if you have an increase in the demand, you will have to achieve an equilibrium between like the equipment requirements and how it is going to be operated. When we talk about buffer preparation, we tend to focus about the steps of buffer preparation and the transfer. And we don't know, or we tend to forget that there are a lot of steps that are involved in this preparation. Some of the steps that are in the life cycle of the buffer are presented here. So the buffer preparation starts with the raw materials reception, the release, and taking a sample. And the raw materials are placed in the warehouse where they are going to be for X amount of time. When the process requests the raw materials, quality has to be happy, and they have to release the paperwork just for someone to go to the warehouse to pick these raw materials. So they have to stack them, put them in a staging area. Then someone will have to scoop them to put them in an intermediate container and move them to the preparation area. Then you have to set up the vessel where they are going to be prepared, add the materials, add the Wi-Fi, mix everything. And once that everything is ready, you can transfer the buffer outside the tank. You can filter, and then you clean the tank. So the buffer is not delivered directly to the process. So normally like you keep it stored for more than 90 days just before going to process. So you require another vessel to be prepared and to be cleaned after too. So what this slide, we mean like there are a lot of time that is involved in the buffer preparation more than just mixing the materials and then just using for the process. So if we just take a look now at the considerations we have to take into the design, there are many considerations from equipment, operational, and layout perspective. So the design has to be able to achieve a balance between the equipment requirements and the scale, and has to provide an easy, like it has to provide a facility that is easy to operate and flexible for new materials. So I know that here there are many considerations, but I'm going to talk about them in a classified way. So if we start with equipment, we need the first consideration that we have to consider is do we want to go single use or stainless steel? Both of them have advantages or disadvantages, and probably the solution is going with a mix of both. So it's true, like the modern facilities tend to go with single use because of the flexibility that they give, and because they are contained vessels, like the risk of getting contamination is lower in these ones. But however, in the end, like the decision is going to be based on size. Like if your buffer volume is less than 3,000, you can select a single-use mixer. But above this volume, you will have to select a stainless steel vessel. In both cases, you should always operate between 30 and 90% of the volume just to allow for a good agitation. And it is always recommendable to prepare like 10% extra than the volume that you're going to use for the process to compensate for the possible losses that you're going to have. Another consideration is what technology to select for this preparation. We will talk about this a bit later. And what's the quantity? So how many stainless steel vessels do we need? Do we need heating and cooling conditions to prepare the buffer? If so, how we consider the jacket, a thermal control unit for this? What are the utilities that we need to prepare a buffer? So for the traditional way that you normally require process air, you require Wi-Fi, and you will have to install a vent. And then what's the material of construction? So stainless steel is not always good for, it depends on the buffer concentration that you will have. Sometimes you will have to go to a higher grade or even an alloy. In terms of operational aspects, you have to consider how much staff like is gonna need it to prepare the buffers that you need, how they are gonna operate, what's the shift pattern, how many materials you're gonna have because you have to allow for space. Are the ergonomics okay for the people that are gonna work in the area? And what's the preparation strategy that they are gonna follow? According to for the layout, you have to consider room classifications. So buffers are normally prepared in Class D ISO 9 clean rooms. For buffer hold, for the storage, like traditionally, they were contained within clean rooms with similar classification. But nowadays, the industry is striving to have them installed in unclassified controlled areas because it's supposed like a large savings in terms of cost. You have also to allow for material and personnel flows in between the two areas. So this is normally done through airlocks. You have to provide for a staging area to place the raw materials that are going to be used for this preparation. And then you have to design the material transfer. So once that the buffer is prepared, it has to be filtered to eliminate any possible bioburden, and it will be done through the wall of the clean room using a pass-through technology, and it's going to be controlled measuring the weight. And then you have also to see how you want the adjacencies. So you want the whole area connected directly to the process, or you want it, or you have to bring it closer to the production area. Well, nowadays there's a changing in demand. So it is true, like when you design a facility, you do it for a specific process, but the facility has to be able to be good for unknown future processes too. So the industry is looking for more flexible and adaptable processes. They want to be sustainable, like Kevin will talk about sustainability in a bit. They want to be innovative, and they want to try to reduce cost, because like all the buffer preparation has like a huge cost associated with them. In terms of the ways of prepare a buffer, there are 4 main philosophies. So the first one, purchase ready to use, means that you outsource the buffer preparation. You buy the buffers ready to use to someone else. The second one is the traditional buffer preparation, that you prepare this multi-component solution at the final required concentration, so it is ready to be delivered to the process. The third one would be buffer concentrates or inline dilution, that you prepare the buffers at higher concentration than required by the process. So this will require an additional step of dilution just to adjust the concentration to the required one. And the fourth one, inline buffer preparation, also known as inline conditioning or buffer stock blending. You prepare the buffers inline from stock solutions at the final concentration too. So if we just go a bit more into detail for each of them. So the purchase ready to use is becoming increasingly common for small facilities because of the advantages that it presents. So this philosophy allows to reduce capital cost, because as the industry is not, the facility is not preparing the buffers, they can save in equipment. So it helps to reduce bottlenecks, and most important, it has advantages in terms of safety, because operators are not exposed to the raw materials. They have less problems with ergonomics, and they don't do repetitive tasks that they would do if they prepare the buffer in-house. However, for larger scale, it has many limitations, because this philosophy, like, it's not very it has problems for the scale, like to be scaling up. It has logistical challenge, because the in-house loses control over the production, and you depend on the market, and then like it has higher cost. If we just jump to the traditional buffer preparation, this is just, you mix the raw materials in a single use or a stainless steel vessel, and you get the buffer at the concentration that is needed to be used with the process. So normally you don't go directly to the process, so you require to hold the solution for next amount of time until it is used. Buffer concentrates is very similar to the traditional way of preparing buffers, but as we said, like, concentration is higher. And even though you are using the same raw materials at the beginning, the same quantities, the initial quantity of Wi-Fi that you use, it's very low in comparison, so that allows to reduce the capacity of the equipment that you're going to use. So the problem or the challenge here is, like, because the buffers are very concentrated, you can have pitting corrosion, so it is very important that you select the correct material of construction for this preparation. So you also need to dilute the buffer before using it, into the process. This sometimes can be done or can be integrated with the chromatography to the chromatography skid directly. And then another thing that you have to consider here is how, like, you have to see how much you can concentrate the buffer. So this is normally a parameter that is calculated in the laboratory, but it's gonna be dependent on two main things. So the first one is the common ion effect. So this means, like, if you have many raw materials with the same ion, you are gonna reduce the solubility of the components. And the second one is gonna depend on the less soluble component that you're gonna have in the mixture. So these things they have to be taken into account when you decide the concentration of the buffer. And the last method, or inline buffer preparation, you have the acid, base, Wi-Fi, and salt, and you blend them inline to get the buffer at the final concentration. And this is done and controlled by analytical instruments such as mass, pH, or conductivity. So what is important here is just you can go directly to the process because you have the concentration already and everything ready to go. So you can avoid having a whole tank, so you can save that capital expenditures. Also, like, you have like individual stock of solutions, like quite concentrated. And as we said at the beginning, like, you only need 10 raw materials to get to 10% of the buffers. So, like, with very small amount, you can produce almost all the buffers that you need. And this philosophy allows you to do that. In terms of, if we compare this with the traditional way of preparing the buffer, it have the advantages, like the footprint that it occupies is lower. It also requires less consumable and requires less labor. So now, do you?
No, I've got another one. Thanks, Maria. So, look, as Maria mentioned, buffer management is a big problem for the industry. I would say the biopharma industry has been developing at a rapid pace. There's a lot of innovation. Buffer prep is completely overlooked. We've seen massive increases in product titers. I would say the example I would have given a few years ago, if you've a 10,000 litre process at 2 grams per litre, you need 20,000 litres of buffer every batch. If you brought that up to 10 grams per litre, you need about 120,000 litres every batch. When I first started using that example about 9 years ago, that was an extreme case. Now we're looking at product titers far higher than that, even at scale, where I'm looking at processes with 400,000 litres of buffer per batch. Granted, that is at the higher end. When a batch is every 2 days, just the amount of material is enormous, but the industry still hasn't changed. One of the groups I've been involved with for the past few years is BioPharma. So for those who aren't familiar, it's a cross-industry collaboration coming together to solve problems of common interest. They published a technology roadmap back in 2017 and identified buffer prep as one of the big challenges. Through that, we formed a buffer prep work stream, which I think was back in 2018. And through that, we designed and built a prototype skid. We did it in collaboration with NIMBLE in the US, which is the National Institute for Manufacturing Biopharmaceuticals. So they helped co-fund this skid. So to give an idea, and again, I'm not going to read through all the names, but when we talk about a cross-industry collaboration, you have engineering designers, so myself as part of the team. You've got skid suppliers, Asahi, Cytiva, I'll touch on that again later. And you've got a lot of the leading manufacturers, your MSD, Sanofi, Regeneron, Biogen, Lonza, and whoever else I've offended by leaving out in the list of names. But it's a really example of trying to design by consensus. One of the things that is out in the market, so the first question we were asked is, there is inline systems on the market, and there was back when we started this work. Cytiva have an inline conditioning system. Asahi Kasei have a buffer stock formulation system. Both of those can do this. You notice both of those were involved in this work stream as well. So this wasn't just about building a skid, which we did, and there was good outcomes from it. it was about trying to prove the technology, that a lot of the benefits I'll talk about this type of technology, any of those skids will do. So it's not that you have to buy this skid. It's trying to increase that awareness. And some of the main reasons we did it were design a system that has consensus. So when you put complex buffer chemistry equations in front of people, they lose the will to live most of the time, but they're very difficult to understand. People don't understand the complexities of it, and it's much easier to put a defined mass of acid-base salt and water together, mix it, check the pH. Also, the costs are very high. So look, that is a disadvantage of this technology for capital cost in particular. And also, people are scared of what's new. Nobody wants to be the first to try a technology, having proven data sets and test results. Ultimately, I suppose the system was designed, it was built, it was tested, and it's installed in the University of Delaware. Again, I'm going to give some highlights here, but for people who are interested, the full design documents, and there's about 4 or 5 papers as well, are on the BioPharma website. Look, for the students, I can send on a link to it afterwards with some of those if you're of interest. One of the advantages with this system, and probably one of the reasons why I talk so much about buffer, is it's in a more non-competitive space. We can actually publish the P&IDs, we can publish the functional specifications, and anyone can access it. The skid itself, this particular one, we could make buffers 8 to 60 litres a minute, connect up to 16 stock solutions. Probably one of the main features that's simplified is it's a mass flow based system. In a couple of slides, I'll compare the different types of control methods. For me, the biggest part of this particular design is it's customizable. So yes, we want to standardize, but different processes will need different number of pumps, different elements. And the idea is we wanted to make a base skid that you can take that and apply it. Say this would be typical for, say, a 2,000 litre bioreactor scale facility, but also you can scale it up and scale it down. And by publishing the engineering details, in theory, you can go to any skid manufacturer and, I suppose, reduce the time to get it to market. The skid itself, WFI would come in through an integrated brake tank. Other systems on the market will bring WFI in from a bag in front of it. Both of those options work. The key there is having a pressure brake. For a mass flow based system, ultimately your final pH and conductivity, which is what we're releasing the buffer based on, if you change the proportion of mass flow, you're going to get a different buffer. Varying pressure in your Wi-Fi would cause that to trip out, hence you need in the brake system. Now, the release on this system is pH and conductivity. We are looking at other approaches, more looking at buffer composition and pretty more PAT type applications that can be built in as part of future skids. We have, in this case, we've got 4 solutions. So different systems on the market operate in slightly different ways. So the Cytiva ILC system will mix your acid and base, then add your water, and then add your salt with multiple static mixers. In our case, the up to 4 stock solutions mix into a single line through a simple static mixer. 2 pH probes. Again, I suppose one of the biggest issues on ILC systems in general is the pH probes. So salt memory effect, pH probe drift. Ultimately, you need to calibrate these every single day, every batch. I suppose they're probably the biggest barrier on these systems. The 2 pH probes help with the salt memory effect of one route for high salt, one route for low salt, and it helps that stabilization time. Why does it matter? So, in terms of the mass flow and what do we need to control? So some of the other systems on the market have different ways of controlling. So in both the Cytiva and Asahi systems, they can do mass flow and they do pH flow and pH conductivity. For our system, we just went with a simple straight mass flow. I would say in development, having the other options is absolutely fantastic and helps you get to a recipe. From what I've seen a lot in production, prefer the mass flow because define controlled input, define controlled output. The big disadvantage with mass flow is if you get variation in your stock solution concentration, the system won't adjust for it and you'll fail your spec. For some buffers are very sensitive to temperature. The majority that we deal with in bulk biologics wouldn't be, but in theory, if you were coming from a hot Wi-Fi loop into a point use cooler, variation in temperature could throw it off. And obviously there's an inherent variation with your pumps and your flow meters. We're using Coriolis flow meters. They're highly accurate, but you do need to control your inputs. It's worth when you use your inline conditioner, your buffer stock blending, you still need traditional buffer prep to make your stock solutions. So, you know, the industry is well used to doing that. So you can get the careful control you need. If you do a pH flow, again, you can vary. In those systems, it can dynamically vary the concentration of the different stocks to hit your target pH. The downside with that is pH probes are far less reliable than a Coriolis flow meter. And similar to pH conductivity, one of the big concerns of the pH flow and pH conductivity from QA and quality is, in theory, you can vary your composition of buffer for every batch. Yes, you're meeting the right pH and conductivity spec, which is critical. But I've seen from a quality perspective, people are more comfortable with mass flow in production. What do we care about when it comes to making a buffer? So look, the group we came together at BioPharma, we picked 6 main things. You have to achieve a stable pH and conductivity. That's a given. If you don't meet the required quality, it's not a viable solution. You have to get to the right target flow rates. We also care about the time to collect the buffer. So when you start up these systems, you're going to have to run to drain until you get into spec. The longer that takes, the more you're literally flushing stock solution down the drain. What's the percentage of stock solution wasted? How reliable is it? So it's fine to get into spec. Can these systems stay in spec? You know, when you're running a downstream operation over a few days, you can't be drifting in and out and have a stop-start process. And also, what's your dilution factor? So, you know, one of the advantages, I know Maria mentioned the common ion effect and multi-component buffers. For a single component stock solution, you don't have the common ion effect. You can go more concentrated on those solutions. Again, brings material construction challenges, or certain aren't great in single use. But how can you maximize that and have your stock solutions last longer? I suppose the results from the buffers at blending system are shown on the screen. Again, it's more just to reiterate, the other systems on the market absolutely perform in an equivalent way, and they do work. What we found for pH and conductivity, we had a standard deviation of less than 1% across the runs. We're able to make all the buffers in spec. We also did offline sampling as well to validate the result of the probes on the skid. And again, you can see, you know, on a zoomed out version over a couple of hours, I suppose it's a very stable, you know, little bit of tracking at the very start, and there's a slide on that later, less than a minute until you get into spec, and then a very stable flow. Again, a pretty more zoomed in example, and you can see the pH and conductivity trends for a typical 50 millimolar phosphate buffer. You can see in this case, we actually started off in spec, but then as time went on, the band got tighter. Generally, for these systems, they work well. They're even better for larger preparations and running longer. You know, if you have very small preps, I suppose they lose some of the efficiencies. Again, similar with flow rate. So on this particular skid, we had a combination of Quattroflow and Lua pumps. We had 2 of each on the stock solutions, and the whole point was to test and compare. It's exactly how you wouldn't design a skid for industry, where you'd look to standardize. But we wanted to try all the different pumps. Is there a difference? I suppose the short answer is they both worked. Yes, there's nuanced differences between them, but both worked. Obviously, you can see that, you know, in the zoomed in versions of flow, yes, there is more pulsing due to the nature of the diaphragm metering pumps. But again, flow within spec, the flow was stable. In terms of time to collect, I would say some buffers go into spec from when you hit the start and the pump start within 10 seconds. I'd say the average was about 23 seconds. The longest, I would say, this graph is from when we'd fine-tuned the pumps and actually configured the skid properly. But even early days, it was less than, we never had to run over a minute before it got into spec. When we look at stock solution waste, you're talking 3-4% of the stock solution ends up going down the drain. Now, That was in our performance testing, which is in a lab where you're making a couple of 100 litres of buffer at a time. Now, where this is important, if you're making 100 litres of buffer and you're running for 30 seconds of flow, it's going to be a higher percentage than if you're making 3,000 litres of buffer where it's still only 30 seconds and then you're running stable for the rest of it. The dilution factors we had in the lab in Delaware were up to 20 and probably as low as 2 or 3. To be totally honest, the chemicals we used were what we could get available from people who were on the BioPharma team. So it was pretty, we took what was available to us as opposed to maximizing it. A lot of the work I've done in the last few years now has been developing approaches to optimize stock solution selection, and I won't bore you too much on the PhD element of it, but there's a lot of good papers out there now showing how you can take it a step further and maximize the benefits. The big difference is the speed. We could make 3,000 litres of buffer in less than 1 hour with this approach. Why does that matter? And normally I'll use this graph as a good example. If you have to make 3 lots of 3,000 litres of buffer, if you had a traditional system, if you started at 8 in the morning, prepared your buffer, and only leave yourself half an hour between preparations, which you'll never achieve in reality, you're into the early hours of the next day before you can make the 3 preps. If you start with an inline system, you spend the first few hours of the day messing about calibrating the pH probes and setting up your stock solution. And then in theory, you can make your 3,000 litres of buffer at about an hour each and be done during the day. Traditionally, buffer prep is 24/7, labour intensive. For large scale facilities, it's still going to be 24/7 and labour intensive, even making stock solutions. And certain buffers like diafiltration buffers, people aren't using ILC systems for that yet. There's more concern as you're further down the process. Chromatography buffers are probably the ideal example. I would say, by running these much faster, for smaller scale facilities, there's opportunities to change the way we operate. Rather than 24/7, you can get to a point where you have a 1 or 2 shift where you're working Monday to Friday only, actually having that time to recover. Even if you need more operators on a per shift basis, ultimately you can reduce the labour count for buffer and allocate those people elsewhere where they're needed. How does it look for a facility? So this is an example layout for a 2,000 litre facility. In the prep area, you've got 2 tanks, 3 single-use mixers, small scale prep area, buffer hold on the outside. For the inline buffer prep systems, there's 2 ways we can do them. We can run them as a buffer kitchen, where you put the buffer prep skid in the skid in the buffer prep area, use that to prepare buffers, and then they go into hold systems and go to the process in the normal way. I would say from a layout point of view, there's not much difference between your traditional and your buffer kitchen. Where there is a difference is on debottlenecking. So this is a good option probably to debottleneck a facility without making wholesale changes to the process. The other way you can do this is doing it on demand. So some of the systems out there, like Cytiva's system, have inbuilt chromatography capability. So your chromatography skid has the ability to do inline conditioning. In that case, now the buffer prep area is making stock solutions. We can get down to 2 single-use mixers, and those mixers would also be used for other buffers like diafiltration buffers or any non-ILC. And then the stock solutions connect to the process, and the process makes the buffer on demand. In this example, you're saving 55% of the space compared to a traditional buffer prep. And again, there's a big push on projects. We need to be more efficient. We need to, there's various sensitivities. We need to reduce the cost of goods, reduce the cost of manufacturing, and reducing the footprint is a significant way to doing that. Also brings down HVAC demand, reducing clean rooms, has sustainability benefits. In terms of economics and environmental, and again, I'm not going to go into a massive level of detail here. On the BioPharma website, there's an economics paper I did back in 2019, which goes through all aspects of this and has the defined numbers and the full numbers. In general, what I found, we did it for 2,000 and a 12,500 litre scale. Again, linked back to the typical processes from the BioPharma technology roadmap. What we found at the smaller scale, the capital cost of inline was higher. The skids are expensive. There's no way of getting around that. But there was savings on operating costs, labor demand, pretty much everything else, and the overall cost of buffer is dramatically reduced. Equally, you see, going with buffer concentrates and inline dilution is far better than traditional. I think my first takeaway is not traditional is the answer. In reality, it's going to be a combination of different approaches. It's not that you'll make all buffers with inline or all with traditional. Once you get up to the very large scale, again, inline buffer prep probably has the lowest overall total cost of buffer and net present cost. The big red there is on the consumables. It's seen as it's red because the cost was higher, but what that really means is you're enabling single use by making the volume so much smaller that now you actually have a choice. Doesn't mean it's mandatory to use single use, but so the red was more of I took a straight criteria of if the volume is below X, it was 2,000 litres at the time, we're using single use. The big advantage, even though you have to prepare your stock solutions, I suppose it'd be quite common that might have 5, 7, 10 stock solutions that can make 20 buffers. So now you have to do 10 traditional buffer preps instead of 20. And each of those preps, because they're more concentrated, can last for a lot longer. What we found is it can pay for itself in 100 batches. Now, can't always convince them the project side at the start and overcoming the initial investment, but the benefits are there, and a lot of companies are using these approaches now. Not as many as perhaps should be. The other one, as well as the economics, we also need to think more about sustainability. It's really important we start to integrate sustainability into the process design. Now, full life cycle assessment is the best way to go. In this case, I'm going to talk to you about some of the work I've done using pretty sustainability or indicators or metrics, looking at process mass intensity, embodied and operational energy. Ultimately, using those metrics, and the reason I use those is they're really easy to integrate into a design process. And when I screen some of these systems, I might look at 150 scenarios. I'm not going to do a full LCA on the 150 scenarios, whereas using some of these metrics means I can build it in. When I look at process mass intensity, it's the mass of materials required to go in to produce 1 kilogram of product. No surprise, traditional stainless steel is worse than traditional single use because I've factored in cleaning. Now, some of the PMI studies that were published in the past haven't included cleaning. The ones I've done have. I think it's a bit disingenuous to exclude it, especially when you're using highly purified water. Inline buffer preparation ended up being slightly worse than traditional single use. When you look at embodied and operational energy, and you could do the same for embodied and operational carbon. Again, a very similar metric. Single use outperformed stainless steel. Inline buffer prep in this case was marginally better than single use. Depends on where in the world it is, where you're getting your stainless steel, what's the embodied energy, how much recycled. I suppose the point is, even with those different metrics and indicators, you're getting similar themes. The thing of most interest for me in the context of buffer prep is the economics and the environmental actually align. So the cheaper one to run is also the more environmentally sustainable one. It's not often we get that right blend. Despite that, the majority of the industry is still using traditional buffer prep. A lot of new facilities now are moving, but we did a survey with BioPharma, and out of the responses, every single one of them, a traditional prep is the most predominant in the network. The industry is slow to change. Why? I suppose difficulty justifying the capital. Again, hopefully some of these papers and some of this work is going towards that. They're deemed complex. There's limited experience and lack of proven performance data. Now, again, that's something we're looking to change through BioPharma and having those industry working groups, but it's still a barrier to overcome. Also, people don't want to be the first to adopt these things. Now, we're at a point now where so many have them, you're no longer the first. But these are the general barriers to change we're finding in the industry and some of the stuff we have to overcome. All in all, what is the future of buffer management? Ultimately, we're going to have to go to a world where we consider buffer in process development. We can't go and just say, this buffer worked. We should be doing some work to simplify, standardize, and optimize. And to do that, I suppose it's important to quantify the impact that will have on design and justify it. I see continuous inline PAT coming in for buffer prep and more technology, increased automation and robotics for material movement. Ultimately, you see a world where we can have a completely automated lights out buffer prep, debottleneck it, and move away from a 24/7 operation. I think there's been a lot of changes in the last few years in buffer prep. It started to get a lot more focus. We still need to go a lot further to actually realize those benefits across the industry. Look, it was a really whistle-stop tour of buffer prep. As it was mentioned there, it's literally my PhD topic, so I pretty could speak about it all day. For those that are interested, I can get some of the links of the other papers sent on, which will go into far more detail. The key takeaway for me is when we're designing a facility, the core process is defined during process development. Yes, we have to design it and make some changes. Buffer systems are probably one of the most customized aspects of it. There's so many different variables, both how you run it and how you design it. And it hasn't been given the focus it needs. And again, right now, buffer accounts for 20% of the cost of manufacture, a massive proportion of facility footprint. And also, it's a non-competitive, it's a common area that if we fix buffer, we can do it across facilities.
So thanks, Kevin and Maria. Very interesting, very topical. So hopefully all the students here in the room with us, the emphasis, I think, was on sustainability. So really important in talking about life cycle and integrating that. So, and really interesting, like that's Kevin's PhD topic. So you summarized it quite well, Kevin. I know you could have spent about 2 days talking about it. So thank you. And Maria, really interesting, I suppose, and to see what the facility shift is and the industry shift is, it's really interesting to see another alternative. So thanks for giving up your time.